Welcome to the first event of the Hugging Face Machine Learning Club India. I am really excited. So is Shaq, so is Lewis. So some logistics before the talk. It's going to be a 1-hour talk. We'll also have a question answer round. And sorry for the trouble of blocking everyone from texting. But submit your questions in the Google Doc and do use your HF username to sign off the question so that we could, reach out to you later with the questions. This is the title of the talk. Lewis is with us. A little bit about Lewis. He is the research lead on the post-training LLMs section at Hugging Face. He is also part of the winning team of the first AIMO Progress Prize, co-developer of models like Zephyr and SmolLM3. And he has also co-authored a bunch of books and courses. So if he's one of the, if not the person to talk about post-training of LLMs. And with that, I shared the stage to Lewis.
Awesome. Thank you so much for the nice introduction, Atreya. Let me share my screen and hopefully technology doesn't fail us today. Can you see this?
Yes. Yes,
Absolutely.
go ahead.
Should I, can you see, there's no Google thing hovering over the
we can see the hovering thing as well. You could maybe just close it and we'll just,
we close it.
Yeah, let's do that. Okay, is that better?
Yeah.
Okay, cool. Yeah, so thank you very much for inviting me to talk about this recent work that we've done with some great collaborators at CMU, ETH, and Numina. And it's about a model that we trained called QED-Nano, which was specifically trained or post-trained to be able to prove mathematical theorems. And the reason why this is like kind of an interesting topic is that mathematics is in some sense like one of the kind of, let's say, simplest domains to study in a way. So even though the problems are very hard, it's one of the domains where we have at least a chance of being able to verify whether the outputs are correct or not. And there's been a lot of excitement in the past 6 months. You may have seen this yourself on Twitter, where various companies like OpenAI and others have shown that, if you extend the kind of models that they have with some, special scaffolds or agentic harnesses, you can actually go beyond just proving, problems in a very narrow case, but you can actually kind of make some non-trivial contributions to mathematical research. And so part of the motivation of this work was to try and understand, okay, can we first figure out how we can kind of teach models to be good at theorem proving? And then can those insights guide us on trying to go beyond just trying to solve self-contained problems and potentially, contributing, ideas towards furthering research more generally. So this talk is, it's a strange format. I'm experimenting with kind of a mind map. So it's basically, as you'll see, it's a big thing with lots of different things to talk about. And I think what I'll do is, Sayak and Atreya might have some questions as we go, and then, it won't be a conventional, slide-by-slide talk. And if you have any questions about anything, just jump in and ask. So the first thing I thought would be good to sort of just ground a little bit about what I want to talk about is kind of like the sort of main recipe that went into this QED-Nano model. So the first thing we had to do was to sort of find some like high quality set of prompts for theorem proving. This turns out to be actually the kind of secret sauce of like almost all post-training. So everyone tends to focus on algorithms or, how good their infra is or their, RL stack and all that stuff. But the thing that actually really makes the biggest impact is actually of the data, right? And so Gia from Numina did a lot of really great work finding high quality problems that we could then use both for doing reinforcement learning, but also for distilling proofs from the current most powerful model in open weights. And that's this DeepSeek Math v2, which I'll talk about a bit. And so once we had these proofs from DeepSeek, we could SFT them, SFT a model with this. But then the other kind of trick in the recipe was to sort of find a way of how we could do reinforcement learning when we don't have a very simple verifier. So if you've ever done reinforcement learning for mathematical problems, you may have seen situations where you say, solve this problem, and the answer has to be like something like a number or a single value, which can then be cross-checked against the ground truth in a fairly straightforward way. But with proofs, it's much harder because the proofs aren't presented as a single value. And so one of the kind of key ideas that I'll be talking about is this idea of using what are called rubrics as rewards to kind of train the model. And so part of our recipe involved using a mix of models from Gemini 3 to GPT-OSS to kind of provide these rubrics that could inform their reinforcement learning training. And then the other thing that we included in this recipe was doing like kind of standard RL, although we were able to show that it works pretty well. Many of these like proofs, they require very, very long reasoning chains. And so here we're talking about, getting the model to kind of have a chain of thought, which is on the order of like 50,000 to 100,000 tokens. And if you try to do RL on these very long chains, it tends to be relatively, let's say, noisy, because basically you have to sort of, you get a final kind of score at the end based on your rubrics, and then you have to back propagate through all these tokens. And this tends to be just a particularly difficult, like long horizon problem. And so one of the kind of key innovations in this work came from our collaborators at CMU, which was this idea of introducing something called a reasoning cache, which I'll explain a bit later, which basically allows, it's like a decoding algorithm, which basically allows language models to have very, very long outputs, which are kind of coherent on long horizons. And the final thing that kind of went into the training of this model was to understand how the final model interacts with different agentic scaffolds that have been developed for mathematical reasoning. And so let me, before we jump into the nitty-gritty, I thought it would be good to sort of motivate a little bit where we were coming from. So just for those who perhaps aren't on Twitter all the time, about, I don't know, maybe it was about 7 months ago or so, no, a bit more, maybe 8 or 9 months ago, there were like these kind of two, let's say, big milestones that were achieved by OpenAI and DeepMind. And the announcements they made was that for the International Math Olympiad of last year, both of their models were able to achieve what's called a gold medal on this very difficult competition. And this is a competition where you have basically some of the most gifted high school students across the world representing their country, and they have to solve 6 problems, 6 very, very hard kind of math problems under some time constraints. And up until then, there had been like a lot of, let's say, progress on like mathematical reasoning using a bunch of tools. Things like, for example, Lean as like a programming language to do some of the verification. But what was like novel in both of these announcements was that they were able to do this without using tools or any sort of external tricks. It was, as far as we could tell, basically like a language model running with some sort of agentic scaffold. And so this was kind of what inspired us to really sort of say, okay, how could we do such a thing using open models? But to give you a bit more of context of like what preceded these 2 milestones, DeepMind had been doing a lot of work beforehand to essentially train language models using Lean. So in 2024, they actually were able to get a silver medal on the Math Olympiad. You can see here. And their approach in 2024 was radically different. So at the time, the approach that DeepMind was taking was to essentially use this programming language called Lean, which is, it's like a general programming language. However, it has built-in kind of verification. So if effectively it has a compiler which will check whether the kind of statements in the program are true according to some axioms that are built into the library, and if the program compiles, it gives you some kind of, let's say, confidence that the actual statement of the proof is correct. And so this is like one way where you can sort of ask yourself, okay, could we scale up like kind of RL using lean as a verifier? And then this would be a way of trying to not have to require mathematicians, like human mathematicians, to kind of grade every single proof and provide signal to the model. And so this approach that they had was called alpha proof. It's a very kind of elegant idea. Basically, they have this pipeline where they first start with what are called informal problems. So these are like standard kind of math problems that you've probably seen in school or university. And then they needed a system, which was essentially an LLM, that would convert these informal problems into these so-called formal problems. And this like kind of formalization is now giving you something that is like suitable for running lean. And then you feed those formal problems into a neural network, which together with some kind of search algorithm is able to generate proofs in lean. And then you can check whether those proofs compile and therefore whether the model was able to correctly prove a given problem or not. And as I mentioned before, they got silver medal, which was at the time also an important milestone. But you can see that already it's kind of like a fairly complex system, right? You have to have, first of all, the lean compiler kind of running in your loop. You need to have a very good formalization system, which can convert problems that are in natural language into this, relatively esoteric lean language. And then you, on top of that, have to have a search algorithm to essentially search over the space of like kind of, they're called tactics in lean, but you can think of them as kind of ways of solving or proving various subproblems. And you need something like kind of like an AlphaZero type search algorithm in there. So although very impressive, clearly quite complex and sophisticated. And I think one of the goals that kind of prompted the later work that they did and also OpenAI was to see just how far can you push just a pure language model in this domain. And so the challenge was that somehow set, and we asked ourselves, okay, what does it actually take to achieve kind of comparable results, given that in both cases we had very little information for both OpenAI and DeepMind at the time. We basically just had a couple of tweets to work from. Maybe before I carry on, are there any questions at this point?
There are some, but not really related to this. Louis, before we go to the next couple of slides, I wanted to ask one of my questions in which I really like the recipe of what is to come in the next slides. And I feel like there are three aspects to this entire project. One is like the data curation part. The other part is talk about how the RL pipeline or maybe even the training pipeline is laid down. And the third part is where you start the training and the infra related problems which comes out. So for a person who is kind of trying to get into some projects, such projects, what is the timeline, or how does one kind of divide their attention to these three aspects to make the best use of the entire thing?
Yeah, it's a great question. I think for projects like this, we really benefited from having not just one person, but like a team of experts. So for example, like if we look at my list of collaborators here, so Jasper, who's here, he is the co-creator of Matharena, which is a very, very popular benchmark. I can show you quickly. This is essentially the kind of, let's say, gold standard of evaluating mathematical capabilities of models today. And so they do a huge amount of work, both creating new benchmarks, but also testing new models when they come out. And so his kind of input into the project was like essential for helping us design the eval part of the problem. Then Gia did a huge amount of work kind of curating the sort of initial set of prompts for the data. And then the folks at CMU, like Yu Chao and Amrith, They then use that data to then augment it with all these kind of tricks I'll talk about in a bit. So generally speaking, I think you kind of can contribute on many different axes. The one lesson I would say today is that models themselves tend to be, I would say, relatively short-lived. As you've probably seen on like,
Right.
various benchmarks like Meta and that, there's always like an incremental update and then all the other models are now outdated. And the thing that really kind of, let's say, stands the test of time tends to be like a very good evaluation that kind of probes some deficiency of the current set of models, or curating data. I know it's not like the sort of sexiest thing to say, but it is generally the case that creating high quality data sets and making them available to the research community tends to be the kind of like highest long-term impact one can have.
Right. I also think Shaik has a
Yeah.
ahead.
I have one question. To what extent do you think there has to be a very tight correlation between the ultimate evaluation metric on which the entire workflow is gonna get evaluated and the evaluation metric that we use when scaling test time compute? I'll give you a very brief example. I'll take a motivation from image generation because it's probably easier to explain. Let's say I want my image generation model to be extremely good at aesthetics, but when I'm throwing more compute during test time, maybe my reward signal is just prompt following. To what extent do you think there has to be a tight correlation between the two? Because in my experience, at least as far as image generation goes, having somewhat a very general metric during test time scaling is often very helpful and helps cover the diversity, whatever that means. In my case, helps cover the diversity more rather than focusing on any specific evaluation metric during test time scaling. So do you think there's any correlation?
Yeah, so one thing that we observed, and I can talk about it a bit later, is that the ability of a model to utilize an agent scaffold, or let's call it like a test time harness efficiently, does depend on the kind of choice of algorithm that you use to train. So like maybe the most, let's say, popular example I can think of is like, you've probably seen like, OpenAI have like Codex models, right? And these are models that are kind of trained specifically in like the Codex CLI, like they're very good at utilizing the kind of surrounding, let's say, context from the CLI. And it's the same thing for these kind of tasks, right? Where you have different kind of scaffolds and they make different kinds of assumptions about what the model should be able to do. So for example, is the model able to follow instructions well to be able to do, sequential kind of generation? And what we found is that if you look at essentially metrics, like for example, we measure reward, right? Maybe I'll just skip straight to a plot to make it clearer. But basically when we did like our initial RL, you get, these kind of like, standard curves. So you have like reward goes up, your kind of output length goes up, and you also see some like, nice gains on the kind of downstream evals. So you can see that like, reward going up is roughly correlated with your downstream evals. So that would be fine if you only care about a kind of single turn evaluation where you just do one kind of rollout per problem. But later we developed another method, well, the guys at CMU did, where instead of doing just a single like rollout per turn in RL, you do multiple turns of rollouts. And so you have this kind of like, kind of sequential series of rewards. And then later we found that when we were scaling the test time compute, that basically you get this kind of, let's say, nice relationship where like, here's the kind of result you get from a single turn evaluation. Here's the result you get from training, for taking a model that was trained with this reasoning kind of cache harness and then evaluating it in the same harness. And then if you then take other harnesses which use many, many more tokens, you get better performance on the downstream evals. And so generally speaking, I think one can say that there is a correlation between the reward and the downstream eval. But in the ideal case, you just train your model in the same scaffold that you're going to run at test time.
Yeah, that makes sense. No, the evaluating on multiple scaffolds, I think I can confirm this. I'm not allowed to talk more because this is a submission. This is a part of a submission, but running multiple scaffolding is definitely more helpful. At least in our case, it's not related to text, but it's related to image generation. Even that helps. So, but yeah, good to know. Yeah, I'm good with my questions.
Okay, cool. So I've talked a little bit about like, okay, the motivation for why we did this. Let me now talk a little bit about kind of like the say where you get kind of data to start such a project. So Gia, who works at Numina, this is a non-profit who have done a lot of impressive work on like open data sets and kind of scaffolds for mathematical reasoning. And him and his team, they developed a very nice data set, which I'll just dig up now quickly. Let's see, data set trained. Okay. So they helped us create this data set, which we called Find Proofs. And basically, like, you have problems that, are sourced from a bunch of like public domains. One of these public domains is called AOPS. It's called the Art of Problem Solving. And it's a kind of a community forum that people use for kind of sharing like approaches to problems to prepare for the actual IMO. And so it's a kind of rich source of candidate problems. And so him and his team were able to kind of take these problems and filter them for quality. And the other one where a large amount of like heavy lifting work was done was to extract so-called Olympiad problems. So in addition to the IMO, there are many kind of regional competitions for like different countries. So as students prepare and train for the actual IMO, there are like, so more like, let's say, national competitions. And these competitions, okay, not great for the hub to fail like this, but these national competitions basically have lots of their problems available online, but they're typically encoded in like PDFs. And so getting kind of like the raw text for those problems and also verifying that everything is correct takes a large amount of work. And so what Gia and the Numina team did was kind of, basically curate a very large number of these PDF problems, and then use a bunch of AI tools to extract the text and the kind of solutions from them, so they could be, amenable for using for training. So this data set was the kind of like starting point for most of our work. And I think what I'll do first is I'll talk a little bit about like kind of what you could do with such a data set. And then I'll talk about how we then used it in this kind of multi-stage training. So let's suppose I look at one of these problems. So let me find, say something like, maybe like this. That's a bit of a boring one. Let me, yeah, okay, this is a kind of nice problem. So here you're given some like mathematical expression involving some like sinusoidal functions, and you're basically asked to prove that the kind of, let's say, corresponding like difference of these terms is equal like to 2 to the power of 4. So this is a kind of representative problem that would be hard to kind of verify as like a single value answer. And so what you can see in this data set is that in addition to having the problem, it has something called rubrics. And I'll go into more detail on this in a second, but just to give you a taste, it's trying to simulate how like a human grader might look at a proof or a solution to such a problem. And if you remember, like, back at university and high school, typically, you weren't just given like a binary score for, is your answer correct or not? You were often given like partial credit. So for example, maybe you get like, the first 3 steps correct of a problem, and then you make a mistake on the 4th or the 5th. And so you still get, some partial credit. And that's the basic idea of these rubrics, which is instead of just penalizing the model as like 0, you didn't get the answer, or 1, you did get the correct answer, you have now a bunch of criteria which kind of ascribe a series of points, which are based on whether or not the proof has, like, for example, referencing this thing called like Demois theorem, or you get 2 points if you can set up this binomial expansion. You get 1 point for using some scaling factor and so on. And so once you have this kind of like checklist, then what you can do is you can ask an LLM to grade the proof of the model that you're trying to evaluate or train, and then it can use that checklist to ascribe points, which then translate into some sort of final reward. So I'll show you kind of in more detail what this looks like here. So this comes from a very, very nice paper from Scale AI called Rubrics as Rewards. And what they showed in their paper was that, like, part of the motivation was like, okay, how do you go beyond, like, the kind of simple verifiable domains where you have things like, test cases for code, or you have, simple single value answers for math. And so the kind of approach they took was to say, okay, we're going to first generate these like rubrics using a combination of LLM and human experts. And we're going to kind of ground these like rubrics in terms of some documents, and we're going to try and make sure that they're self-contained and so on. And then once you have those rubrics, you can do reinforcement learning by basically taking a prompt, which in their case, they were focused on like medical tasks. You have these like criteria that, like, did the model response kind of identify the diagnosis and so on. And then it's the standard like GRPO training loop. So you generate rollouts, you kind of grade them with the rubrics and the LLM judge, and then you update the model weights based on the so-called advantages. And so the very nice thing of this approach is that not only does it generalize to sort of non-verifiable domains like, medicine and, other broader categories of science, but it's actually like a very good test bed for theorem proving, because even though the proofs could be verified by something like Lean, it's much better to give kind of fine-grained feedback using some sort of LLM judge. So this was like a kind of key paper that influenced the sort of early way we thought about setting up the problem. And we also saw some like kind of other follow-up work by Alan AI, where, let me just get rid of this. Okay, where they had shown that if you use rubrics for training, you can actually use this to train, really high performance models for deep research. So in the Alan AI paper, it was called Dr. Tulu. They were trying to understand how do you create something like a kind of open model that is like good at this kind of deep research feature that you may have seen in things like OpenAI's ChatGPT and so on. And so in their case, they had the situation where they wanted the rubrics to kind of be dynamic. So it was a little bit more sophisticated than the Scale AI case. But crucially, it showed that you could do this kind of, very long horizon kind of like RL, because deep research involves many, many steps of reasoning, and that you would get something that was, very, very performant. And so in the end, what we did was we took these ideas and we created something which looks a bit like this. So basically, we took the problems that we had curated with Numina, and then we generated these series of rubrics for every one of the problems using Gemini 3. And then this gave us these kind of criteria that every proof should satisfy. And then we did reinforcement learning with those rubrics. So now you've got the prompt, you've got the model that is generating the rollouts, and then you're getting now graded. Every single rollout is now getting graded by an LLM, which in this case turned out to be GPT-OSS. And doing that gave us these like kind of nice curves that I showed you before. If we go, yeah. So doing this on like the Quen like 4B reasoning model was able to kind of, give us these nice learning curves for the rewards, and also to kind of, non-trivially improve the performance on two, popular downstream evals for evaluation. So this was like a good sign that using rubrics as rewards for theorem proving actually works. And before I jump into the next thing, I'll see if there's any questions.
Yeah, there's a bunch of questions. Orithro, do you want to ask yours, or should we take a couple from the audience?
We could take a couple from the audience. I see some. Do you have some in mind, Shai?
Yeah, I'm gonna pick one. So this is from Nitin. Nitin asks, are we bottlenecked in eval by always having to create novel questions or proofs to avoid memorization in large models, which eventually get distilled into the smaller ones? At what point is the eval dataset unreliable for the rubrics?
Yeah, that's a really, really good question. So I think the simple answer is it depends a bit on the model scale. But it is generally the case that benchmarks that are public tend to be most susceptible to like overfitting, partially because once a benchmark is identified by the community as being something that is like worthwhile to show improvements on, then you will tend to see the next iteration of models are like dramatically better at that benchmark. And that doesn't mean that people are like cheating by putting in, the problems in the training set. But it does mean that generally a particular type of task has kind of been, let's say, data augmented or synthetically generated to kind of match the benchmark. And then this then kind of gives you that overlap. It's a good thing to maybe talk a little bit about how you do evaluation for theorem proving. So basically, there are very few like good benchmarks for measuring like the theorem proving capabilities of models, and almost everything up until recently relied on this idea of having the lean compiler act as the kind of source of truth. And to the great credit of DeepMind, the same team that trained the model that was able to get gold at the IMO, they released a really, really good benchmark called IMO Bench. And in this benchmark, they have a bunch of different categories which cover kind of different elements of theorem proving. So IMO Answer Bench is kind of like the conventional way we measure math capabilities, where you have a single value answer and you just check against a verifier if it's correct. But they also provided 60 problems that were like, human written and, carefully curated and graded for correctness, which were then the kind of basis of a large part of our model development. And they also crucially provided something called grading bench, which is a way of measuring or calibrating the ability of LLMs to overlap with like human kind of grading capabilities. And so you can see here in their paper, they have like a nice plot showing that if you basically use like Gemini as an LLM, you have a fairly high degree of like overlap between the human graders. So this gives you some confidence that you can use like LLMs as graders. However, one of the critical things, which is partly related to the question, is that you need the grader to be like, I would say, roughly as good as the model that you're evaluating, right? Because if you're trying to solve an extremely hard problem, like imagine like a very, very difficult open problem in mathematics, and the proof is like sufficiently complex that the grader is unable to even understand it, then you're not going to have this kind of nice correlation between the LLM and the humans. So this particular benchmark at the time it was released wasn't yet saturated. You could see that like Gemini was getting like, what was it here? Gemini Pro 2.5 was like a bit under 75% on the basic problems and under 25% on the hard problems. But now, since this benchmark has come out, you can see that like, for example, DeepMind's latest kind of model, which is a mix of like DeepThink with some scaffolding, is getting like, you know, almost full saturation. So what this generally means is like, as a field, when the benchmark gets saturated, you have to come up with the next frontier of like hard problems. And right now, probably the like best known evaluation for probing like the absolute limits of mathematical capabilities of models is something called frontier math from Epoch AI. And what's very special about this benchmark is that none of the, let's say, well, very few of the problems are like publicly known. So you can't really hill climb this benchmark in the same way that you can other benchmarks. And they even have like a very cool subset of what are called like open problems, where mathematicians have contributed, you know, real research problems that haven't been solved. And then you're basically, you know, the goal is to see, can the community using any sort of like, you know, LLM techniques contribute to that. So sorry for the ramble, but long story short, it depends at what point on the, let's say the model capabilities you're probing. So for example, if you're looking at something that is on the scale of like Gemini 3 or GPT-5, then you can still use this benchmark and get meaningful signal. But if you're now training something which is more capable than such models, then you're going to have to find some alternative. And this is an ongoing cat and mouse game of like, you know, building the next generation of evals that then inform the capabilities of the others. And actually, one last point, if you look at Math Arena, this is quite instructive. If you look at things like Amy, so Amy is kind of like a simpler version of the IMO problems. And basically now the models are getting 100%. Like there's a few like cases, but like, you know, GPT 5.2 kind of like perfect score basically. And so this tells you that at this point now, Amy is basically a low signal benchmark. And even Amy, I think 2026, you can see it's just not hard enough for the current generation of models. Okay, next question.
I think for the, we would just let you proceed with the next couple of slides, and then we move back, like circle back to the questions.
Okay, cool. Great. So we had now the rubrics, and we now had a very good eval choice from DeepMind with IMO Bench. And I want to comment a little bit before I dive into training on basically like one thing that kind of informed the way that we generate the rubrics. So there's a very, very nice paper from Wenji Ma and others at Berkeley and these other institutes, where they took this idea of like, you know, rubrics and so on, but they really did like a very, very careful analysis about what types of things you should consider when you're trying to apply this to mathematics. And the idea here, as we've seen before, is that you have a problem, you have some like marking scheme with some number of points, and you may or may not have a reference solution included. And so what they did in this paper was they took a bunch of, at the time, kind of like frontier models, and they looked very carefully at like what happens for each different model if you basically don't provide any context except the problem. That's what the none row is. What happens if you provide the reference solution? What happens if you provide just the marking scheme? And what happens if you provide the reference solution and the marking scheme? And so you can see that, for example, like they have like a quality column which measures, let's say, the kind of overlap and agreement with human annotators. And you can see that, like, you know, none of these models are really like kind of consistent among themselves. So it's kind of like the choice of like model that you use for generating rubrics can be more or less sensitive to some of these choices. For example, Gemini does like a lot worse than O3 if you provide the reference solution, for example. Whereas like, let's say DeepSeek R1 performs really bad if you provide the reference solution or just no additional context. Whereas GPT-5 tends to kind of, you know, perform pretty well across the board. So what we did is we took these different choices that they had explored, so whether you provide the reference or not, and we ran our own kind of like internal kind of cross-check on a bunch of like human gradings that Jasper from Math Arena had created. And what we found was that, generally speaking, not providing the reference answer worked quite well for our grader. And in particular, for generating the rubrics, we decided to use Gemini 3, partly because we knew that, like, kind of in most of the downstream evaluation today, we were going to rely on things like IMO bench. And one of the things that we wanted to avoid was like kind of shifting the model really far off from the kind of downstream eval by using a very different grader. And so Gemini was like kind of like the natural thing to use. But it would be interesting to sort of explore, you know, what happens if you pick different kinds of models to generate different kinds of rubrics? Do they produce, like, you know, very different outcomes? It's kind of something that we haven't explored yet. So we've got rubrics and we've now got evals. And so that's where we did this like kind of initial set of like standard RL. So I assume most people are kind of familiar with like reinforcement learning for language models. But just to give you a very quick recap, essentially what we do is we take the model that we're trying to optimize, we sample some series of rollouts or completions from the model. We then have some way of assigning reward to each one of those rollouts. We compute something called the advantage, which is kind of like the mean, like the mean or the centered mean of the rewards. And then there's a kind of loss function that is used to kind of update the weights of the model. And so, you know, doing this gave us these kind of like nice, these nice curves. But as I mentioned before, you can see here that the rollouts are getting pretty large, right? And they're getting into the range of like, on average, like 30 to 35,000 tokens per rollout. And this actually introduced like a whole range of like kind of, let's say, infrastructure challenges. And I want to talk a little bit about that before diving into how we went beyond the vanilla RL. So I want to just show you a little bit this nice diagram here from, there's an open source framework called Verl. And what they kind of highlight in a lot of their documentation is that if you're doing like reinforcement learning and you're trying to do things in like a synchronous fashion, then typically you're in this like upper left-hand corner and you've got, you know, something that is generating your rollouts. When it finishes a rollout, it then, you know, puts them in a queue of messages. And then once you've got like a full kind of mini batch, now you can update the weights, which are these like yellow bars. And so if you look at this kind of synchronous thing, you basically have to wait for every single rollout to finish before you can form a batch. Then you do the gradient updates, update the weights. And this is very inefficient because, as you can see in this example, the rollouts, they all have like kind of different lengths. And so while you're waiting for the rollouts to finish, the GPUs that you're using to do the model updates or the optimization are basically idle. So you're basically wasting a lot of compute while you do this. So the thing that like people kind of explored shortly after these synchronous algorithms were so-called asynchronous algorithms, where you can kind of see them in the upper right-hand side. And the basic idea here is that you still like are generating, you know, all these rollouts, but instead of waiting for like a full batch to finish, you basically create kind of like concatenations of like these mini batches. And then once you've got this like large batch, you can then do the gradient update. This is faster because you're able to generate a kind of a larger like queue of messages before you do the gradient update. But it has some kind of additional complications because now the model that you're like optimizing is not the same model that generated the data. And so there are some tricks that people use to make sure that, you know, your training is stable. And this is like faster. This tends to be about 30% faster than doing synchronous reinforcement learning. But you're still affected by the fact that you still need to wait for like, you know, the last kind of, let's say, rollout in your batch to finish before you can actually make, you know, the complete batch to do the updates. And so what is like today kind of like the sort of, say, state of the art is to go like what is called, say, fully asynchronous. And when you do something like fully asynchronous, that's something like the kind of bottom right diagram, where you just have GPUs that are kind of continuously generating rollouts. And as soon as these rollouts are put in the queue, you form these mini batches. And at some point, you just say, we're going to do a model update, even if we don't have a complete mini batch. And even if the models that we're generating, you know, a particular rollout haven't finished. And so this kind of like design is fairly radical because you're updating your model that is generating data in flight, which means it's maybe has generated like half a proof, and now you're updating the weights with some new weights which came from a previous model update. So it's quite off policy, they say, which means that there's like kind of a mismatch between the model that is generating and being optimized. But it's been shown by a bunch of like different papers and organizations that this works. For example, Mistral were one of the very first kind of labs to sketch out the architecture for this. And so you can see here, you've basically got like all these generators generating rollouts. You've got a bunch of the trainers, and all these diagonal lines just represent an update of the model in the RL process. And this is kind of to date, probably like the sort of fastest way you can do reinforcement learning in this like asynchronous manner. And it was something that we ourselves had to adopt, because when we started the project, we explored using some synchronous RL algorithms, but because we're generating proofs, these proofs are very long. And so some proofs might take 35,000 tokens, some proofs might take 10,000. And so because of these like kind of like stragglers where some take much longer to finish than others, you need something which is kind of continuously able to update. And so for like the RL stack that we adopted, we used something called Pipeline RL. This was an open source library developed by ServiceNow. And if you're familiar on your history of deep learning, you may also recognize that Dmitry Badnow is one of the core inventors of this, who also is the guy who kind of invented attention. So it's quite a cool contribution to the research community, and this was the main framework that we used to scale up our RL training runs. Okay, so we had I've mentioned before we had these good results, but now we wanted to sort of understand how can we kind of really scale the kind of length of these rollouts to very long proofs. And so to do that, our collaborators at CMU had independently developed something called the reasoning cache. And this is a very cool and relatively simple decoding algorithm, which is designed to kind of allow language models to generate very, very long rollouts without losing coherence. And so the basic idea here is that you in a standard kind of decoding, you have an input, you generate some number of tokens, and you terminate. But here, what they do is you take your input problem, you get the model to generate a chain of thought, and then you take that problem and the chain of thought, and now you feed it into a separate model or the same model to summarize. So it kind of summarizes its current, let's say, attempt and what has worked, what hasn't. And then you take that summary and now you feed it as a prefix into the next step where you've now got the problem and the current kind of status of like, you know, what has been solved so far. And then you generate a new chain of thought, and you just do this sequentially. So you do this for like, you know, some number of steps, and now you're able to basically get the model to kind of coherently reason over, you know, effectively, you know, 1 million tokens while being coherent. And so in their paper, they showed that this works very well for like kind of like instruct models. So just doing like a reasoning cache with RL on like Qwen instruct models worked very well. And so we took these ideas and then we applied them to now our theorem proving. And I'll give you an example of what this reasoning cache looks like. Okay, so here's an example of like, you've got a problem. Here's the math problem. This is like the prompt. So you've got the problem, and the model is told whether or not there's a summary from a previous attempt. And then if like there's no summary, then your task is to just solve the problem. And if you have a summary, then you have to improve on this attempt. And there's like some kind of loose, like, you know, general principles about like verification or proving it in a different way or exploring different strategies. So this is kind of the initial prompt to the model. And then you'll get this like, you know, big like chain of thought with like 5,000 tokens. And then at the end, you get like, let's say, the final answer from the first step. So this is kind of like, you know, now a proof of the problem. Then in the second stage of the reasoning cache, you say, okay, I've got this attempted solution. Now, what I'm going to do is I'm going to see if I can kind of condense this into a summary. And so here we've got like the kind of solution from the model. And when you do all of this, you'll get something like a summary, which is like almost like a note of the model to itself. Like I started by substituting this, then I did this, then I did blah, blah, blah. And then I defined some new function, and then I did all these things. And so this is kind of like a condensed, you know, for those of you who are using like coding agents, it's like compaction. You've got some way of like kind of, you know, taking the history, compacting it into like a kind of concise summary, and then that feeds into the next stage of the problem, where now the model is given the same problem, but now it's got this like full summary of what it previously had tried or attempted. And so if you do this for like multiple, you know, steps, you're able to kind of consistently improve the summary of previous attempts. And then this gives you the ability to kind of, you know, reason over long horizons. And so when we did that, we were able to, let me find the curves. We were able to get this kind of interesting result where basically the kind of reward, so using the exact same, you know, data set, everything else is held fixed. You get this kind of like, you know, non-trivial improvement in the training reward coming from the ability of the model to do this kind of like long-term reasoning. And then if you look at like the kind of, let's say, how the reward evolves across these terms of the reasoning cache decoding, then you see that, you know, the successive turns, the reward is higher because it's benefiting from those like, you know, previously generated summaries. So this gave us like a nice kind of like boost in performance, both in the rewards, but also on some of the downstream evals. And that was kind of in some sense like, you know, the starting point of our final recipe. And I know we've only got like a few minutes left, so maybe I'll take a question before I jump into the final part about agent scaffolds.
Yeah, I think I have already selected a question from the audience. So it's from Dheeraj. Dheeraj asks, since QED-Nano uses self-refinement within brackets reasoning cache and recursive solution aggregation at inference, both based on its outputs, how do you ensure it improves reasoning rather than amplifying earlier mistakes or hallucinated proofs?
Yeah, that's a good question. So we don't have an inbuilt mechanism to like mitigate like hallucinations or to amplify these issues. I think generally the main signal comes from the reward that is ultimately ascribed by the grader. So for example, we saw before that we've got where are we? Yep, we've got here. So here we've got basically the model that we're optimizing, and then we've got GPTOSS acting as the kind of proxy for the human grader. So as long as, like, let's say the final stage of the reasoning cache is producing, let's say, proofs that are ascribed some sort of like high reward by the grader, that's the signal that the model gets is kind of on the right track. One thing we did do is that we used a small Quen instruct model for the summarizer because it was much faster to use an instruct model for summarization than a chain of thought model. So I suppose if you wanted to really do this like kind of in a sophisticated way, one option would be to train the kind of summarizer and the generator together, like jointly as the same model. This would give you some handle on like maybe mitigating the amplification effect, but in general, we didn't see too much of that in our particular case.
Do we want to allow one more question before you jump into the next one? We have 3 minutes left.
Let me jump quickly, and then I'll take the next one. So
yeah, cool.
Just to sort of wrap up the final thing that we did is like, okay, we had this like nice reinforcement learning recipe. We had this nice decoding algorithm with the reasoning cache. And the question was, okay, how can we squeeze the like absolute maximum performance from this 4B model? And so the natural thing at this point is to say, okay, can we do distillation from a larger model? And about the time that we started this, DeepSeek released what was called DeepSeek Math V2. It's a model that is comparable to Gemini and other models in terms of its like mathematical capabilities. And we then did a very simple SFT on top of that. And you can see here in these curves that you can, almost double the performance of the Quen 4B thinking model just by doing SFT on these reasoning traces. Now, the problem was that although you can kind of get this very significant improvement, if we look at the tokens that are generated by this distilled model, they're really, really huge. So you can see, for example, that on solutions which it is able to prove correctly, it's requiring something like 50 to 60,000 tokens. But when it makes a mistake, it actually gets this huge never-ending chain of thought of like around 120,000 tokens. And so this is a problem because you don't know in advance whether a problem is like solvable or not. And it's a general phenomenon that is known when you do distillation on small models where they tend to overthink. They tend to say, lots of like, I should try this idea. Oh, wait, I should try this other idea. And even when they get the answer, they will still keep thinking beyond it. And so what we did is we basically took this SFT model, which had very good performance, but it had this like unfortunate consequence of having very large numbers of tokens in its output. And then we applied our kind of like RL recipe on top. So we basically did the same reasoning cache training, and this gave us something which I can probably show here. Which, was basically, best in class or close to state of the art for its weight, across a bunch of these different benchmarks. And the sort of cherry on top was to take that model and then put it in an agentic scaffold. And we explored a bunch of these in parallel. And I won't go into them in lots of detail, but basically, if you take the final model that we RL'd, if you do a single turn evaluation on this IMO proof bench, it's like 40%. You get a kind of modest improvement from the reasoning cache. But then if you're willing to spend, you know, order of like over 1 million tokens per problem with these different harnesses, you can get quite close to the performance of Gemini 3 Pro. But I think I'll stop there and maybe take final questions.
Cool. Maybe before we delve into this further, it might be helpful for folks to quickly have some establishment on scaffolding. Like scaffolding could mean many different things to many different people. So
Sure. Let's do that. Do we have 5 minutes?
Yeah, sure. I mean,
okay.
Yeah,
okay.
Sure.
Cool. All right. So let's talk about scaffolds. I'm going to draw some pictures. Okay. So like, let's suppose I have a prompt. Let's make it green. And now I've got like, you know, my LLM. Let's make it blue and put some text here. So this is LLM. And okay. And then usually, you know, we then generate some output here, right? So this would be, let's just make it clear, prompt. Oops. Okay. And then we can then call this product. Okay. So this would be like the most naive thing that we do. And it's the thing that we, you know, anyone who interacts with LLMs in like, you know, their like the CLI and stuff, it's kind of this thing, prompt, input, rollout, output. So a very, very simple concept of a harness or a scaffold is like, okay, how can we increase the amount of inference time compute that is used for the LLM to improve the final answers? So one very simple technique is called best of n. And basically what it amounts to doing is you just sample from the model multiple times. So you say, I'm going to now generate not just once, but I'm going to generate, you know, multiple times. And then I'm going to have like some kind of criteria to kind of determine which one of these rollouts is the best one. And that criteria might be something as simple as like just looking at the majority vote. What is the majority common answer? Or it might involve having some external verifier, which then checks which one of those is preferred. So this is best of n, and it's like the kind of, let's say, simplest scaffold you can imagine. Then the sort of next more complicated thing you could imagine is like, okay, let's, instead of doing all those parallel rollouts, we're going to do like kind of like a sequential improvement. So maybe you take my rollouts here, and now there's a step where I have some output, and maybe there's like kind of like refinement here to refine, oops, refine, and then you do another rollout, and you do, oops, you do this again and again. So like one thing you might think of is like, instead of doing this like parallel kind of scaling of test time compute, you now have like a sequential scaling where you just do iterative steps. This is a bit like the reasoning cache idea. So when we talk about scaffolds or like agentic scaffolds, they are roughly speaking exploring whether you're scaling along these axes of parallel compute or sequential compute. And the best ones tend to be some hybrid version of this. And a very good paper by these folks at Mila and elsewhere was using this like recursive self-aggregation. And they have a nice picture here, which is kind of getting close to what I was talking about, where you can do like parallel scaling or sequential scaling, but the kind of best of all worlds is hybrid scaling, where you do a mix of both. And for them, what they adopted in the end or developed was something called recursive self-aggregation. where you generate some like initial like kind of population of candidate solutions. You now aggregate those solutions with an algorithm they have, and then you feed the question and these aggregated solutions into the LLM again to generate the next set of like population candidates, and then you just do this multiple steps. And so, for example, here for the aggregation, it's like, okay, you're given a problem and several solutions, some candidates are correct or whatever, aggregate the useful ideas and produce a single high quality solution, reason carefully, blah, blah, blah. And so this is kind of how like you basically are taking the best of both worlds, where you're scaling your compute test time in parallel, and then you're refining it sequentially and then doing it so forth. This is just one of many types of scaffolds, but roughly speaking, it just boils down to one of these two kind of paradigms. And then there are like many, many sort of, you know, small things you can explore on how you actually do that scaling. I don't know if that answers your question, Sayak, but that's roughly speaking what I had in mind.
Yeah, it does. I had two quick things that I wanted to add. One, more than 120 folks are still in the call, even though we did surpass it by 6 minutes, which is kind of a thing, I would say. Even like for a talk that covers complex topics like math, I gotta give it to you. So that's great. Second, it's probably a bit of a bitter news. Best of N still rocks in the image generation world when it comes to test time scaling over fancy, you know, search techniques and trajectory-based techniques. Third, a hybrid approach like you mentioned, where you can control the depth of the search as well as the breadth of the search, is actually also very helpful. So some of these findings equally translate to image generation as well, but probably best of scan is still sort of the ruler in our world. So
okay, so best of N is still the tough baseline.
Very, very tough. But yeah, as I mentioned, we are already 7 minutes over, so we are not going to keep you any longer. And I really wanted to thank you, and I'll leave it to Orithro to say the final words before we call it a day and hop off.
Yep. So thanks, Lewis, for being the first person to kind of jumpstart our entire suite of talks for HFML Club India. Thank you to all the people, 120 plus people viewing. So we are really thankful. We also got your questions inside of the tab and the Google Doc. So that is really nice of you to do. We'll be sharing some more updates in our socials. So please follow us. And yeah, thanks for all the questions. So with that, I would like to end this call and see you all in the next one. Thanks.
Great. Thank you very much for having me.